All right, let's continue. So you see the 6 degrees of separation which the video talked about, this article which you see on my screen, it was published by Facebook on in 2016, and that time Facebook had 3.5 degrees of separation. So that is how much more and more closely connected we are getting, and how they computed this was, let's take a look at it. So this graph shows it. So what this graph shows you is on the x-axis you have average degrees of separation. So how do you calculate average degrees of separation? You take every person, you calculate his average distance from every other person on Facebook. So as an example, you take me, then you take yourself, see what is the distance between me and you on Facebook, then you take every other person in the same way and you take an average. So this shows you the distribution of this average path length. Degrees of separation is nothing but the average shortest path length here from one node to all the other nodes. So what you see here is on x-axis is this average path length and on y-axis is the number of Facebook users. So it tells you how many users have average path length of just 2.8, how many users have average path length of 2.9. So as you can see that the minimum average path length is close to 2.8 and maximum average path length goes around something 4.6, right, and where the average mean is 3.57 here. All right. Any comments on the video, anyone? Now I'm unmuted, right? You people can hear me. Yep. Okay. So see, actually I asked each of you to type a +1 in the chat window when finished watching. So I was waiting for all of you to finish. Okay. Anyways, so with this, let's proceed. So in this video, this person talks about two models. So one is the random model and another is the small world model. So the one which he made by putting these buttons in a circular fashion. So what we'll do now is we'll look at how do we create such networks with the help of Python iGraph, and when we create them we'll also talk about the properties of such networks. So wait a minute, I'll just open my Jupyter notebook and we'll get started. Okay. So I'll start with importing the iGraph package. As I told you, the package name is same in both Python as well as R. Yeah. So once I have imported this package, so what I am currently doing is I want to make a random graph. So let's say I want to create a random graph on 10 nodes. How do I do that? As we discussed before, what we do? Anyone? So how many edges are possible on 10 nodes if it's an undirected graph? Can someone tell me? So what I'll do is
I choose to.
yes, right. So how much is that? N is 10 here. 45, right? And choose 2. All right. Uh, so we create an empty graph here. So let me show you and let me print G here. So this statement G equals to graph, it creates an empty graph for you, and as you can see this graph is undirected here. It has 0 nodes and 0 edges. So first of all we'll add 10 vertices to this graph and then we'll see how can we add the edges. So let's add 10 vertices, d dot add vertices 10. This will add 10 vertices to this graph. Let's do this. As you see now, the number of vertices has changed to 10. If you want to see this graph here, what you can do is use this function of igraph, which is called this plot function. When you do ig.plotg, you can see all your 10 nodes here in this graph. And see, this figure is actually quite big, so let me make it small. So I'll change the size of this box in which this figure comes, and I'll make it 300, 300, right? So that you can see it all at once. So you can see all these 10 nodes here of this graph, right? But we don't see the labels of this graph. So basically these nodes here, they are numbered from 0 to 9, and I also want to see the node numbers. How can we do that? So to do that, I want to associate a label with every node, and that what that label should be, that label should be the index of each node. So first of all, how do I see the nodes of this graph? So we use this object which is called vertex sequence. Let me show you. So if you print g.vs, it returns you an igraph vertex sequence object, right? So instead of printing this object, I'll convert it in a list and then show you. Right. So this is what this vertex sequence object has. So it has all your 10 nodes. As you see here, this second entry here, it tells you the index of the node, and this third entry here, it stores the attributes of the nodes if they are present. Here we don't have any attributes, right? What I want is, I only want these indices which are 0, 1, 2, so on and so forth for each node. So what I'll do is, I can iterate over each vertex in this vertex sequence. So take a look at this. If I write a for loop here, so let me do for each in g.vs. So I'm iterating over this vertex sequence, and let me print each dot index. So this is how you can iterate over it. So this gives me the indices of all these nodes. So I'll repeat, you iterate over this vertex sequence object. When you iterate over it, you are iterating over each node, and over each node I see the index of each node, right? And I want the label for each node to be this index. So what I'll do is, I'll use a quick list comprehension here. I do indices equals to, I hope you have seen this kind of coding in Python. It's just a shortcut way of doing what I previously did. Have you seen this before? Creating a list like this? So essentially what this line is doing is, take a look at this code. So I take indices as an empty node, and then I could have done for v in g dot vs indices dot append v dot index, right? I hope you at least understand this code over here, right? This is something which you can easily understand if you know Python basics, right? This line is just writing these 3 lines in a single line. So this is called list comprehension. All right. Anyways, you can explore it further after the class. So once I have done this, let's print indices here, and you can see that this indices here is a list of all the vertex indices. Now I want these vertices to be labeled as indices. So what I'll do is simply include an argument here which is called vertex underscore label, and these labels I'll pass a list here for these labels, which is the same list as indices. So if you do that, you can see all the labels of these vertices here, right? Okay. Next, what we want to do, we want to add some edges to this graph. So let's first of all see how do I add edges here. So for adding edges, we have this function similar to add vertices. We have a function which is add underscore edges, and what do you pass to this function is, you pass it a list of tuples, and each tuple is an edge here. So I pass it a list, and in this list I have all the tuples which I want to add. So let's say I want an edge from 0 to 2, and let's say I want an edge from 2 to 6. right? Okay, so in this graph, the number of vertices changed because I have run this code many times. So let me just run it from the beginning. So here I am adding 10 vertices, and if I execute it, you see these 10 vertices here in the graph. And now I want to add edges between these two pairs. So I have added edges. Once I have added edges, let's plot this graph again in the next line, let's say. So you see both of these edges over here. So that is how you add edges. But what we want is, I don't want to add edges manually like this. So as we discussed, we want to create a random graph. So I want to add edges randomly. How do I do that? Any idea, anyone? So with the code which I have shown you here, you can very easily do that. Any idea how can I add random edges to this graph? So this is the graph I have, and instead of adding these two edges, I want to add some random edges. Essentially what I want to do is, I want to iterate over each possible edge, right? And for each edge I am going to flip a coin. If it is head, I'll put that edge in this network, otherwise not. So let me say, for each edge, flip a coin. If I get head, put that edge in the network, otherwise not. So how do I do this? I'm going to import random package for this, right? So take a look at the code and then it will make sense to you. So what I'm doing is, for I in indices, I is an iterator which goes through every index, and let me say for j in indices, and what I do is r equals to random dot uniform, or rather I can use random dot uniform, or I can also use random dot random. Yes, random dot random. And if r is less than 0.5, I add an edge from I to j, otherwise I don't add any edge, right? Now can someone explain this code? What is happening here? Is this code clear to you? Why this code will give you a random graph? You can also write your answer in the chat window. Okay, do you understand this code? Type a +1 if you understand it, so that I can proceed, so that I know that you have understood this code. Okay, Sakshi has understood it. Both Sakshis have understood it. All right. So three people have understood it. What about others? Do you see what is happening here? So for each possible edge, right, I go from, so I goes from 0 to 9 in this case, and j also goes from 0 to 9 in this case, right? So I go, so let me write it down. Okay, I'm getting more responses. Okay, does anyone see a problem with this code? Do all of you think this code is correct or is there some problem with it? Remember that this graph which we are making is undirected. If anyone tells me the problem with this code, I'll appreciate it. I'll give you some bonus marks for classroom participation. Anyone?
Is it like it can have like multiple edges between two nodes?
Exactly. Right? I can have multiple edges between nodes here. So what is happening? I and j, I can have multiple edges as well as I can have self loops, right? So I and j will initially be 0, 0, then there will be 0, 1, so on and so forth. At a time it will be 1 and 0 also, right? So that way it can give you multiple edges. Here it might put an edge between 0 to 1. It might also put an edge between 1 and 0. So we can have multiple edges and we can have self loops also, which we don't want. So what should we do for that? If I want to remove such kind of edges?
And maybe we should check if ij is already an edge. Then only we should apply g dot edge, add edge.
That is one thing we can do. So if an edge already exists, do not add that edge. That will solve the problem of if there is an edge like 1, 2, 2, 1 will not be added. And we can also how to resolve the problem of self loops. If I equals to j, then I shouldn't add an edge, right? So what I'll do here is I write a simple statement which will take care of both of these cases. So I do all this part only if I is less than j. So if you see it previously, this code it was giving you permutations. If you write this one line here, if I is less than j, it will give you all the combinations only, right? So all the cases where I equals to j and I greater than j, those pairs will be discarded. So let me put all this code at a single place. So first we create an empty graph. We add vertices to it. We find the indices here. 10 vertices. After that we do this entire process and then we can plot this graph, right? So you can see this graph over here. This is the network which we got. Okay, in this case you see we are flipping a coin for each edge. So the probability with which we are connecting is 0.5, right? It's a fair coin. So with 0.5 probability we add an edge, with 0.5 probability we don't add an edge. So we can also change this probability. Let me make it zero point 0.1. It means that the graph will be sparser. The probability of each edge now is less. So you see now if I create r equals to 0.1, sorry, p probability is 0.1, we see only these edges here. I hope you understand this part, what I am doing here. This is not so straightforward. So I am taking a random number between 0 to 1, and if that random number is less than zero point 0.1, only then I add an edge. This actually means that I am adding an edge with the probability which is zero point 0.1. Why? Because what is the probability that you generate a random number from 0 to 1 and it will be less than zero point 0.1? That probability is zero point 0.1, right? What is the probability that I generate a random number from 0 to 1 and the value is less than 0.4? The probability is also zero point 0.4. So that's the logic based on which we have added this edge here. Okay, let me run it once again, and now you see a different graph, and this time see the graph is connected. So even with a probability of 0.1, most of the times you will find this graph to be well connected. Right. And then we can increase this probability so you get a quite a dense graph, right? But all of these graphs are random graphs. The edges will keep changing every now and then when you create a graph. Next, we should look at how do I compare this random graph with the actual real world graph. So as the video told us that random graph is not a very good representative of the real world network, Why exactly? So let us see it. So for seeing this, what I'll do is, let's actually take a real world network. Let's create a random graph corresponding to that real world network, and let's visualize both so that we can see how different they are. I'm going to use a network which is Karate Club network, which we also used last time.
Excuse me, ma'am.
Yes, tell me.
Ma'am, in this graph, we still have multiple edges or
No,
like
no, no.
between 4 and
Actually,
8.
we don't have multiple edges. The problem is with the visualization. So you see here
All
these
right.
nodes 3, 4, 8. So yeah, one node is
Okay,
running
that's
from,
basically between
that's
3 and 8.
overlapping, right? Yeah,
Okay.
so this is between 3 and 8. So yeah, we can check this using, let's see, g dot es. So like g dot vs, we have g dot es, and say for each in g dot es, print each. So basically I'm trying to see each edge in this network. How do I see the two vertices here? Let me see. Long time I use this package. Let me just look at it quickly. Mm, mm, mm. So you can always look up these things with Google search, and one or the other place will find your. Okay, so we can use this function here, get edge list, right? We can do it like this. So let's use it here. Let's say e dot get edge list, and you can see all the edges here, right? All the tuples here, right? So yeah, you won't see any overlapping edge here. It's just because of how this network is visualized. So that is the advantage which RI graph offers you. So if I have plotted it in RI graph, I could actually pull this for here and there, and I could see whether there are actually multiple edges or not. So R offers you nice visualization. All right. So now let's compare a random graph to a real world network. What I'm going to do is use the same graph which we used in the previous class, which is the Karate Club network. So I have the data set already on my system. Let me show you from where can you get it online. So there are many different formats in which you can find these networks. Yeah. So this is one place from where you can download this network. There are a whole lot of other websites from where you can download it. Let me actually show you the file. So this particular format, it is commonly used in graphs. It's called a GML format. I'm just seeing how I can increase the size here. Okay, I hope that it's readable. If not, I'll tell you. So what it does is it gives you all the nodes in the graph, all the node IDs. It's just a way of representing a graph, and then it gives you all the edges. So this kind of representation, it is called a GML file. So many a times when you look at graph data sets online, you will find these .gml files. So currently I have this file on my system oh, which I'm going to use. Just a second, I just closed the window by mistake. What was the file name which we were working with? Does anyone remember? Yeah. So let's first have a look at this karate network here. So I'm going to load this karate network with a function which is read underscore GML. So this function, it is used for reading the GML files, and let me pass the link of the file here. And then let's plot and see this first. Right, vertex.label. So indices is a variable which we created for another graph. So instead of doing that, what I'll do is I'll pass the same thing here, v.index for v in karate.vs. Right. So I'm passing indices as this vertex sequence. Yeah. Okay, just a second. So here you see this graph. Now I want to create a random graph and I want to see how much different the random graph is from this graph. So let's first look at the number of nodes and number of edges in this graph. So there are, you can see this entire information here also. There are 34 nodes in this graph and 78 edges. And currently it's giving you a adjacency list representation. You can see all the edges are listed here. Okay. So we have 34 nodes and 78 edges. Let me ask you a question now. So just a moment, I'll share this screen from my iPad for a while. Just give me a second. All right. So we have this graph here, which is the karate graph, which has 34 nodes and 78 edges. What I'm looking for is, and this graph looks like something we have already visualized it. What we are looking forward is we want to create a random network, right, with the help of the algorithm which we just discussed, that flip a coin for each edge and make the graph. Right, so this random graph, it is also having two attributes, I'm sorry. So we were making this random graph on the basis of what should be the number of vertices, which we initially took to be 10, and second was what is the probability with which you should place each edge here. Now I want to create a random graph which looks like this karate network. So definitely the number of nodes I should have is 34 here. Can you tell me what should be the P here so that I get approximately 78 edges in this network? What should be P such that the number of edges is 78? Any idea? How can we compute that? So you see, if we have P equal to 0, number of edges will be 0. If we have P equals to 1, how many edges will we have? We'll have 34, choose 2 edges, right? Something like this, which is a huge number, 17 into 33. I want only 78 edges. How to compute P?
Ma'am, you can do 78 by 34 C2.
78 by 34C2. Okay, let's see from where this came. So let me simplify this problem. So let's say I have n nodes in a random network and probability is p. Can you tell me what will be the expected number of edges in this graph? You are correct. What will be the expected number of edges? A simple probability based question. So see, what we are doing is on n nodes we have n choose 2 edges, right? This is the total possible number of edges. For each edge we are flipping a coin, a biased coin, which gives you head with probability p, and if you get a head you place that edge, otherwise you don't place an edge. So on an expected, how many edges will you get? Have you heard of indicator random variables, anyone?
Will be P into NC2.
P into n choose 2, right? Exactly. How do we get this? So can I say that the number of edges which I'll have, so this is the number of edges, let me represent it by m. Can I say that m equals to, I'm just solving it more mathematically for you so that you can see from where we got that formula which Sakshi is telling us, plus x and choose 2. What is this here? Each of the x's here is an indicator random variable. Do you guys know what is indicator random variable?
No, ma'am.
No. Okay, what's a random variable?
Yes, ma'am.
Okay. So can you tell me what's a random variable?
Yeah, it takes any values in a certain range.
Right, it takes any value in a certain range. Indicator random variable is nothing but a binary random variable which can have only two values, 0 and 1. That's all, right? So each of the xi's here, it's an indicator random variable xi. It can take these two values, which is 1 and 0. Let's say 1 with probability p, so 0 will be with the probability 1 minus p. So can I say the number of edges I have? It is x1 plus x2 plus x3, so on and so forth up to x and choose 2. So if I get first edge here, I'll get a 1 here. If I don't see an edge here, I'll get a 0 here. So I'm simply adding 1 corresponding to all those edges for which you got a head here. And to solve it further, if you want the expected value of m, it will be expected value of your first indicator random variable plus expected value of your second indicator random variable, so on and so forth. And your expected value of an indicator random variable is p. And I'm not going into a lot of details here. You can read about this further. So it will be p plus p and choose 2 times. So which is p into n choose 2. You can also look at it more simply. So let's say the value of p is 0.5. So what we are essentially doing, we are tossing a fair coin and choose 2 times, right? And we are trying to see how many times I'll see heads. So let's say this and choose 2 was 50. Just as an example, let's say and choose 2 is 50. I want to see how many edges will I get, right? How many edges will I get? Same as the number of heads which I'll get. How many heads I'll get? It's 50 into 0.5, isn't it? 0.5 is the probability of a head here. So we are just generalizing that. If it's a biased coin and probability of a head is 0.1, in that case how many heads will you see? You will see 50 into 0.1 heads. So that is from where you get it. So if you look at the expected number of edges here, so the expected value of the number of edges is p into n choose 2. So what is p going to be? P is going to be n choose 2. Am I right? So m is n choose 2 divided by m. Right? Is that what we have written here? It's slightly opposite of this, right? Am I correct? Does this seem right?
Ma'am, I don't think because density would be an extremely large number and probability is usually between 0 to 1.
I'm also seeing what I just did wrongly. Correct. Let's see here. We have and nodes. We have and choose true. Possible edges. Each edge can exist with a probability p. So finally, the number of edges which I'll get will be p into and choose 2. Right? Yeah. So p will be m divided by n choose 2. My bad. Right? This will be p. Any doubts? Anyone here? Okay. So with this in mind, we'll create the karate network. Now we know the number of nodes, we know the number of edges, so we have a fair idea of what the probability should be. So we'll create a random graph based on this formula. Just a second. I think time's up, right? So I'll stop here. We'll take it from here tomorrow. If you have any query in this formula, do let me know. So take a look at it after the lecture in your own time. Yeah. So if you have no queries, you can leave. We'll take it from here in our Thursday's lecture.